Alkanes are compounds of carbon. Carbon is an element from group 4 of the periodic table. This implies that it has 4 electrons in its outermost shell. For stability, it needs to bond with other elements such as hydrogen. Hydrogen bonds with the carbon to form methane, which is the first alkane. Alkanes occur naturally in petroleum and biomass. Decaying biomass produces biogas, which contains over 60% of methane. Two carbon atoms can also bond to form a carbon-carbon single bond. This gives rise to the next alkane in the line, that is ethane. Ethane has 6 hydrogen atoms surrounding 2 carbon atoms. Likewise, we can form the next alkane in the series, which is propane. From that, we can have butane. We can also have pentane and also hexane for 6 carbon atoms. How do the chains build up? Let's start with methane. To go to ethane, we need to push out one of the hydrogens and slot in CH2. From ethane to propane, we need to push out the CH3 and slot in a CH2. From propane to butane, likewise, we shall push out the terminal CH3 and slot in a CH2. And likewise, we can go to pentane in the same manner. We realize that to move from one compound to the next, we need to add a CH2, which is the methylene group. The methylene unit is equivalent to 14 daltons. This implies that one molecule differs from the next by 14 units of molecular mass. Such compounds which differ from one another by the number of methylene units are said to be in the same homologous series. We can represent alkanes with a general formula in which the rule is for a given number of carbon atoms, the number of hydrogen atoms will be twice the number of carbon atoms plus 2. In this case, if n is 1, it means that we shall have methane. If n is 2, we shall have ethane. If n is 3, we shall have propane. And for n equal to 4, we have butane. Likewise, we can build very long chains by just using the general formula. How does carbon compare with silicon? Like carbon, silicon comes from group 4 of the periodic table. Silicon forms silenes, whose general formula mirrors that of alkanes. The first silane is SiH4, which is analogous to methane, and the second is disilane, which is analogous to ethane. Silicon, however, cannot form very long chains like carbon, because the silicon atom has a longer atomic radius, which makes the silicon-silicon bond relatively weaker. Physical properties of alkanes. At room temperature, alkanes can exist as gases, liquids, or solids depending on molecular weight. As molecular weight increases, the strength of the van der Waals forces of attraction between the molecules increase. Alkanes are immiscible with water. In other words, they are hydrophobic. Substances dissolve in water when they form electrostatic attractions with water molecules. The energy given out when these electrostatic attractions are formed is used to break the intermolecular forces of attraction between water molecules, which are essentially hydrogen bonds. Water molecules are held by hydrogen bonds, while alkanes are held by van der Waals forces of attraction. For solubility in water to occur, First, the van der Waals forces between alkane molecules need to be broken. Second, the hydrogen bonds between water molecules also need to be broken such that the alkane molecule can fit between the water molecules. The alkane molecule should then form electrostatic attractions with water molecules. However, since alkanes are nonpolar yet water is polar, the molecules cannot form stable electrostatic attractions. As a result, the alkane molecule is repelled. And this explains why alkanes are immiscible with water. As a result, we observe that when alkanes are mixed with water, we shall have two layers, the water layer and also the alkane layer. Alkanes combine with other substances in nature. For example, when burnt in oxygen, an alkane yields carbon dioxide and water vapor. Excessive use of alkane-based fuels increases the amount of carbon dioxide in the atmosphere, and this results in environmental challenges such as global warming and formation of acid rain. When burnt, alkanes produce heat and light energy, and for this reason they are used as fuels. In addition, they are also used as fuels in internal combustion engines to propel our automobiles. Alkanes also combine with chlorine in the presence of ultraviolet light to form chloroalkanes and hydrogen chloride. The reaction with the chlorine follows three main steps. In the first step, we have the homolytic cleavage of the chlorine-chlorine bond to form chlorine free radicals thanks to ultraviolet light. This step is called the initiation step. In the second step, the chlorine free radicals react with methane to form the methyl free radical and hydrogen chloride. The methyl free radical is highly reactive. It combines with the chlorine molecules to form methyl chloride or chloromethane and a chlorine free radical. This stage is called the propagation stage. In the last stage of the reaction, we have termination, in which two free radicals annihilate each other to form molecules.